So here's Sophie the dog hanging out right over here, just chilling. This is from a couple years ago. And all of a sudden, Sophie gets up and bolts. Why? Maybe for the same reason that guy gets up and bolts. Oh, there's an earthquake. Takes off. Where are the donuts? Go get them. Well, he's going to get all the donuts. Wait a minute. Why is it snowing inside? Well, that's kind of what this video is about. Not the snow inside, but in this video, we're going to get into the basics of earthquakes. So in this video, we're going to get into four things. We're going to talk about what causes earthquakes. That's called elastic rebound. We're going to talk about the anatomy of an earthquake. We'll talk about seismic waves, or energy that's carried from an earthquake. And we'll also talk about how earthquakes are recorded. Make sure you take good notes. I'm going to check your notes for a stamp on your sheet tomorrow. All right, so let's talk for a second about why earthquakes happen. I stole this from my daughter. It's one of her hair ties, and it's elastic. Which means that if you pull it and you let go, it goes back to its original position. This is exactly what causes an earthquake. There's some sort of stress, meaning there's a force that's applied to rock. Let's go ahead and apply tensional stress. And these rocks get pulled apart. That's what tensional stress is. There's only so much stress these rocks can handle before they snap and they bounce back. Now when they do, the energy that built up in them after they were pulled, when they snap and they bounce back, they release that energy back into the ground, and this is what causes an earthquake. So an earthquake is caused by the buildup and release of stress within strata, and that buildup can happen because of tensional stress and then it snaps back, or it can happen because of shearing stress and then it breaks and snaps back. Here's an animation to show exactly what we were just talking about. This red line here is the fault zone, meaning this is where movement's going to happen between this big piece of strata and this piece of strata. And this is also going to be a strike slip or a lateral fault, where this piece of strata is going to move this way and this block of strata is going to move this way. So if we play the animation, you're going to see the road gets distorted and bent, but notice it doesn't break right away. But there's stress building up between the strata, and then all of a sudden it breaks. And when it breaks, notice how the road goes back to its original position. It snaps back. And that snapping back, that release, that buildup and release of energy is what causes an earthquake. This process is called elastic rebound. All right, so let's take a couple notes about elastic rebound. We're first going to apply stress to this undeformed strata. This strata is going to move this way. This strata is going to move this way. The red line defines where the fault is. So we apply some stress, or we apply force to the rock, and it's going to cause the rock to move and bend. And right now there's a lot of energy that's being stored up in the ground. These rocks can't take a lot of pressure before they snap, and eventually when they do snap, you're going to have a release of stress. And this is what causes the earthquake. The earthquake is caused by a buildup and then a release of stress once we have that break along the fault. But then notice that the rocks went back to their original shape. They didn't stay at their original position because there was movement along the fault. But the rocks that were bent, they went back to their undeformed state. This is called elastic rebound. And elastic rebound is what causes the rocks to snap back to their original position after there's breaking along the fault. Energy gets released into the ground and it causes an earthquake. All right, so let's talk about the anatomy of an earthquake. Here we have our footwall, and here we have our hanging wall. A little bit of a review. This would be a normal fault because the hanging wall has dropped compared to the footwall, which looks like it moved up. Here we have this rise, this cliff. This little rise here is called a fault scarp. And this is any cliff or rise that is formed due to faulting. They can be big, they can be small, as big as mountains, as small as just a little hill. But it forms when one fault block drops or rises above another. So it can be a cliff or a hill formed by faulting. Next we have this fault line. And the fault line is simply the fracture on the surface of the earth that you see that happens because of faulting. So that's the fault line right there. Next thing we have is the epicenter. The epicenter. The epicenter is the place on the surface of the earth where you feel the ground shaking during an earthquake. And it's different than the focus, where the focus is the place inside the earth where the earthquake originates. And that's a really key difference. The focus is where the earthquake originates inside the earth, and the epicenter is the place on the surface of the earth where people would first feel it. It's always directly above the focus. Next, we have this line right here. We've already defined it before. It's called the fault plane. This is where movement happens along a fault inside the earth. And then lastly, we have this word over here, seismic waves, or these words over here, seismic waves. And seismic waves are energy released during an earthquake. All right, next let's get a little more details about seismic waves. Again, seismic waves, that's energy that travels through the earth. And something that's important about that is that seismic waves travel in all directions. Up, down, left, right, they radiate in all directions when an earthquake happens. Not just straight up to the surface of the earth, but all throughout the earth. And there are essentially three types of basic seismic waves. And again, this is energy released from an earthquake. The first one is called a P wave. P wave stands for primary wave. Primary, the word primary means first. And so this is the first energy to be released after an earthquake occurs. And these guys are also the fastest. That's why they're the first, a primary. Think of primary grades or a primary grade school. Those are the first grades that you go through. So P wave, primary first. So they're also the fastest. They're compressional. And what I mean by that, kind of like how a slinky moves back and forth and springs back and forth, it causes rocks to do the same thing. It causes rocks to squeeze back and forth and squeeze back and forth. So that's what compressional means. There's a compressional movement that causes rocks to squeeze back and forth in whatever direction the wave is traveling. They're the weakest. They don't cause a lot of damage. It wouldn't break this house down at all. But it certainly would crack it up a little bit and cause some damage. And they travel through solids and fluids. And what I mean by that is this. If you remember, we have the solid lithosphere. And then underneath that, we have the asthenosphere. So P waves can travel through both the rigid solid lithosphere and the fluid asthenosphere. Now let's compare these to S waves. S waves, also called secondary waves. Why are they secondary? Because they're a little bit slower. After an earthquake occurs, the first energy that would be felt would be a primary wave, and the next type of energy that would be felt would be a secondary wave. And again, they travel a little bit slower. These slower waves have a shearing motion. And what I mean by that, instead of compressing rocks side to side, they pull rocks in opposite directions. So they pull them up and down at the same time. They pull rocks up and they pull rocks down at the same time, like this rope all the way down here. They have this shearing motion where they pull rocks in opposite directions. So compressional will squeeze them, and so compressional waves will squeeze things together where shear waves will rip them apart. These waves are also stronger. They have a lot more energy associated with them, but a difference is that they only travel through solids. You'll only see this energy travel through the lithosphere and not the asthenosphere. And the last type of seismic wave to talk about are L waves. L waves are surface waves. These guys are the slowest. And they're combinations of both S waves and P waves. So rocks are ripped apart and squeezed back together through the P wave motion, but then they're also pulled and split in opposite directions because of the S wave motion. So we have this ripping apart motion in all directions. That makes these the strongest, and they're also the most damaging. Because they travel along the surface of the earth, they only travel through solids. Again, the solid lithosphere. In fact, if you were in the ocean and an earthquake occurred and you were floating in the water and the earthquake happened right below you on the bottom of the ocean floor, you would not feel the earthquake when you were in the water. All right, lastly, let's talk about recording earthquakes. This is a machine called a seismograph. And a seismograph is simply a machine that will record earthquake activities. It can be a physical machine or it can be done by a computer. And then after that machine detects earthquake activity, it will record it on a piece of paper and it will show that energy on something called a seismogram. So the seismogram is the record of earthquake activity, and the seismograph is the machine that will record that record. Okay, so in this video we've talked about 4 things: elastic rebound, the anatomy of an earthquake, seismic waves, and also recording earthquakes. Feel free to email me with any questions or get a hold of me on Edmodo. I'm going to check your notes on this for a stamping your sheet tomorrow.